Seeing at nanoscale. What is meant by seeing at nanoscale? Seeing at nanoscales means that we are seeing objects of the size as small as 1 nanometer to 100 nanometer. That is, 1 nanometers equal to 10 to the power -9 meters. Examples of objects at nanoscales are virus particles and the size of atoms. We seeing small objects use the following devices. We can use the human eyes, optical microscope, transmission electron microscope, TEM, or scanning tunneling microscope, STM. Resolving power. What is meant by resolving power? The resolving power is the ability of an optical device to distinguish clearly two objects that are close together. Why does every optical device has its limit of resolving power? The reason is that an optical device has a circular aperture. Usually, this is the lens for light to pass through. However, due to deflection, a bright circular disc is surrounded by a series of bright and dark rings. Hence, the overlapping of the diffraction patterns affects the resolving power. What is weighted criterion? Weighted criterion states the limiting resolving power as follows. 2 points, 1, 2 can just be resolved when the central maximum of the diffraction patterns of one object coincides on the first order minimum of the diffraction patterns of the other objects. From the diagram, these pictures fulfills weighted criterions. And for this picture, the 2 points, 1, 2, cannot be resolved. And for this picture, these 2 points can be resolved clearly by the eyes. Mathematically, weighted criterion can be represented by the equation theta equal to 1.22 lambda over d, where theta is the minimum angular separation between the objects 1 and 2 that just can be resolved. D is the diameter of the aperture, and lambda is the wavelength of the light used. Note that smaller angular separations theta we have greater resolving power. Also, smaller wavelength of the light, we have greater resolving power. And the greater the diameter of the aperture, the greater the resolving power. First, human eyes. The resolving power of a human eyes, let S be the separation between the two objects. D be the diameter of the pupil, that is the aperture. Lambda is the wavelength of light used. R is the distance of the objects from the eyes. Theta is the angular separation of the objects to the eyes. From Rayburn criterions, we have the minimum angle, theta minimum, equal to 1.22 lambda over d. Because R is much greater than S, therefore S approximates equal to R theta. Example 1. A picture is 2 meters from a man. Two small objects in the pictures are separated by 1 mm. The wavelength of the light is 6,500 nanometer, and the size of the pupil is 5 mm. Part A. The angle obtained by the object to the eyes, theta, is approximate equal to S over R equal to 10 to the power negative 3 over 2, which is about 5 times 10 to the power negative 4 radian. Part B. The minimum angular separation that can be resolved by the eyes is theta minimum equal to 1.22 lambda over d equal to 1.22 times 6500 times 10 to the power negative 9 over 5 times 10 to the power negative 3, which is equal to 1.59 times 10 to the power negative 3 radian. For part C, because theta is smaller than theta minimum, therefore the two small objects cannot be resolved. Let's see an optical microscope. The light waves passes through the condenser lens, and the condenser lens converge the light waves to the specimens. The objective lens and the eyepiece will magnify the image seen by the eyes. Look at the diffraction patterns occurs when light passes through the objective lens. Also, the wavelength criterion, theta equal to 1.22 lambda over d, still holds, where d is diameter of the objective lens. Also, the greater the diameter of the aperture, that is, the greater the diameter of the objective lens, the image will be brighter, since more light can pass through the lens. Example 2, an optical microscope uses light of wavelength 6,500 nanometer. With a lens, the lens means objective lens of aperture 2 cm. Part A, find the resolving power of the microscope, that is to find theta minimum, which is equal to 1.22 lambda over d, equal to 1.22 times 6500 times 10 to the power negative 9 over 0.02, which is equal to 3.97 times 10 to the power negative 4 radian, which is equal to 3.97 times 10 to the power negative 4 times 180 over pi degree, which is equal to 0.0227 degree. For part B, the separation between successive pixels S is equal to 1 over 1000 cm, and the distance is r equal to 0.2 meters from the lens. Therefore, the angular separation between successive pixels is theta equal to S over R equal to 1 over 1000 times 1 over 100 meter over 0.2, which is equal to 5 times 10 to the power negative 5 radian, which is smaller than theta minimum. Therefore, the pixels or the dots in the picture cannot be resolved by the microscope. Example 3. A specimen is viewed by an optical microscope of wavelength 6,000 nanometer. The objective lens has an aperture of diameter 6 mm and is placed at 2 cm away from the specimen. A. The minimum angular separation that can be resolved by the microscope is 1.22 lambda over d, which is 1.22 times 6,000 times 10 to the power negative 9 over 6 times 10 to the power negative 3, which is equal to 1.22 times 10 to the power negative 3 radian. For part B, the minimum resolvable length is S. From the diagram, we see that the minimum resolvable length is equal to R theta minimum, which is equal to 0.02 times 1.22 times 10 to the power negative 3, which is equal to 2.44 times 10 to the power negative 5 meters. For part C, for the length at nanoscales is of order of 10 to the power negative 9 meters. Since the corresponding minimum resolvable length is found to be of the order 10 to the power 5 meters only. Therefore, the microscope cannot be used to observe details of materials at nanoscale. Next, let's see transmission electron microscope, TEM. Let's look at the structure and working principle of TEM. From the diagram, in the TEM, electron beam is first accelerated in the electron gun. The condenser lens is an electromagnet which converge the electron beam. After the electron beam passes through the specimen, the electrons are collected by the objective lens, which is also a magnetic lens, while the projection lens is also a projection magnetic lens, will magnify the final image formed on the foreign screen. The kinetic energy of the electrons will change to the light energy shown on the foreign screen, which is mixed by phosphor. Let's revise the functions of various components in a TEM. Electron gun, which emits electron beams and accelerates them to a high speed. The condenser lens, it is electromagnet, which produces magnetic fields set up by the currents in the coils. These magnetic fields act as convex lens to converge the electron beam. The specimen, when the electron beam passes through the specimens, they are scattered at different degrees depending on the variation of the density of the specimens. The objective lens, this is a magnetic lens which is used to collect the electrons for image formations. The projection lens is also a magnetic lens which is used to magnify the image formed on the screen. The screen is a foreign screen used to capture the image. Ke of the electrons change to light energy. There are limitations of transmission electron microscope. The first limitation is that the specimens should be thin enough for the electron to pass through. Second, only two-dimensional image can be formed. Thirdly, parts of the specimens will be damaged by the electrons during transmission process. Let's compare optical microscope and transmission electron microscope, TEM. First, optical microscope use visible light as the wave, and TEM use electron as the wave. Second, optical microscope use convex lens to converge and bend the light. However, TEM use magnetic lens to converge and bend the electrons. Also, the resolving power theta for an optical microscope is smaller than the resolving power of a TEM due to the wavelength of the visible light, lambda, is the order of 10 to the power -7 meters, which is larger than the de Broglie wavelength of electrons, which is about the order 10 to the power -10 meters. Since smaller wavelength has smaller theta minimum, which has greater resolving power, therefore the resolving power of an optical microscope is smaller than that of a TEM. Example 4. A TEM uses a beam of electrons of wavelength 0.02 nanometer to examine a specimen. Part A. The Broglie wavelength lambda equal to h over square root 2m e v, which is equal to 6.63 times 10 to the power -34 over square root 2 times 9.1 times 10 to the power -31 times 1.6 times 10 to the power -19. V substitutes lambda equal to 0.02 times 10 to the power -9. We got the voltage of electron gun for accelerating the electrons, V, to be equal to 3,770 volts. Part B. If the electrons have different speed, then the final image will be blurred. Part C. Why TEM does not work for fake specimens? Because electrons cannot pass through fake objects. Part D. In order to increase the resolving power, that is, to decrease the minimum theta, we have to decrease the wavelength of the electrons, that is, to increase the accelerating voltage. Example 5. The anode voltage is 200 kV. The Broglie wavelength of the electrons equal to h over square root 2m e v, equal to 6.63 times 10 to the power -34 over square root 2 times 9.1 times 10 to the power -31 times 1.6 times 10 to the power -19 times 200 times 10 to the power 3, which is equal to 2.75 times 10 to the power -12 meters. Scanning tunneling microscope, STM. The structure and working principle of STM. A STM has a tiny probe with tip at atomic scale. When the probe moves horizontally, the tip scans across the specimen's surface at a close distance. When a small voltage is applied across the tip and the surface, electrons jump between the tip and the specimen surface, produce a tunneling current. When the distance between the tip and the surface increases, the tunneling currents will decrease. The graph of tunneling current against horizontal positions shows that if the distance between the tip and the surface is small, the tunneling current will be large. On the other hand, if the distance between the tip and the surface of the specimen is longer, then the tunneling current will decrease. By studying the variation of tunneling current with horizontal distance, the shape of the surface of the specimens can be studied. Note that STM only works for specimens with conducting surface. Therefore, only metals can be studied by STM. Next, the resolving power of STM depends on the tip of the pupil. A finer tip has greater resolving power. Next, the working principle of STM is completely different from other microscopes, so its resolving power is unaffected by diffraction. Let's compare transmission electron microscope TEM with scanning tunneling microscope STM. For TEM, is used to study the internal structure of the specimen. For STM, is only used to study the surface structure of the specimens. Next, TEM only provides two-dimensional image, and STM provides three-dimensional images. Next, TEM only works for thin specimens, and STM only works for electrically conductive surface. Lastly, the resolving power, or we say the resolvable size for TEM, is as small as 0.1 nanometer. For STM, the resolvable size is even smaller, which is 0.01 nanometer. That means an STM has higher resolving power.